All right, so today we're going to be looking at forces on a slope. All right, so what we've been looking at so far is, let's say that I have we'll make it a 15 kilogram object, box maybe, sitting on just a horizontal surface. We worked with the assumption that the force of gravity equaled the normal force, how much the ground pushes back up against the box. And, that's true. That's not an assumption that's been proven time and time again. When you step on a scale, really it only works because you push down on the scale and the scale, uses a spring to push back up against you. All right. And for the most part, so long as any applied force was equal to force friction, this thing would not move. Today, though, we're going to look at what happens when we're not on a flat surface. So let me draw. So that's horizontal. Let's say we have this angle here. Let's say that's a right angle. Let's say this is a 30-degree incline, all right? And I have a box sitting on that incline. I'm not going to put any numbers to this box yet, but without even looking at that, I have some forces on it. For instance, I know that, and I'm going to draw my diagram a little bit differently this time, all right? So bear with me. In this case, let's pretend like my point for my box is still on Earth. It's still being pulled straight down. So I'm going to even say like that's the middle of my box. This box is being pulled straight down towards the center of Earth. We call that force of gravity, or weight is another way you might see that. In this case, though, our surface that we're sitting on isn't horizontal. My normal force is horizontal to the surface it's on. So in this case, my normal force is kind of going that way. Like that's my force normal because it has to be perpendicular to the slope it's on. With this in mind, I can see like these two things aren't going to be equal because they're not going in opposite directions anymore. So instead, I need to break my force of gravity up into two vectors that form perpendicular angles to each other. I would even say this is my force of gravity in the y direction. This is my force of gravity in the x direction. So how can that be y and x if they're, at angles to each other? Essentially what we're going to do with this triangle right here is we are going to rewrite it. So that's my f of g. I could do that a little bit better. Let's go straight down. All right, I should probably have labeled that f of g. This is my f of g in the y direction. That's my f of g in the x direction. All right, that's a right angle. So essentially what I did is I've simply taken my f of g. I know that I have to be worried about this line right here, which is perpendicular to that slope. With that, I can break my f of g into those two component vectors, and if I even turn it, if I move it clockwise just a little bit, it'll line up with this. This, though, doesn't give me a whole lot of information, even if we were working with straight up numbers. But there are some geometry proofs that would say this angle here is equal to this angle here because it intersects at a right angle here. All right, so this 30-degree angle, that means this angle right here is 30 degrees. Now I can go through, and if I know the force of gravity, I can figure out these two things right here. So let's say, like, if I want to know Fg of y, I'm just going to need to use trig, I'm going to use SOHCAHTOA, I'm using everything. So we know that in this case, my FGY, when we did all the kinematic stuff, we typically assumed our y value was our sine, x was cosine. In this case, since I'm looking at a different triangle, remember, SOH, sine of theta is equal to the opposite. So I'm looking at the side opposite my angle, opposite over hypotenuse, FG. CAH, cosine of theta is equal to adjacent, so adjacent to the side over the hypotenuse. All right. So we kind of just flip those around. So I could even say, I'm going to back up a little bit. So we just said, all right, we just said sine of theta is equal to opposite, sorry. So force of gravity in the x direction over the hypotenuse, right? So if I want to get FG of x by itself, I would just multiply both sides by force of gravity. If I wanted to get my force of gravity in the y direction by itself, all right, let me start over. There we go. We said cosine is adjacent over hypotenuse, so in this case the adjacent's the y. And to get FG of y by itself, we just multiply both sides by f of g times the cosine of theta. All right, that gets us these two values. What we're going to find here is that the normal force is just going to be opposite whatever the force of gravity in the y direction is, okay? Because force of gravity in the y direction is pulling in this direction. The normal force has to be opposite that. So it's also going to be at an angle, but it's in line with FG of y. It's just the opposite value. All right, so let's go ahead. Let's put some numbers to some things and see if we can't figure some stuff out. So let me scroll down. Let's say that we're going to work. Let's pretend that shark fin's actually at a 90-degree angle. All right. And let's say this time we're working with a 35-degree angle. Let's say that we have, and we set a box down. I'll even say it's a 15 kilogram box. I think I use that for a lot of masses. All right. I want to know what is the normal force on this. All right. So in this case, diagramming a little bit differently. Normal force goes that way. Weight, or F of G, is going that way. All right. This I can calculate. I'm on Earth. So F of G is equal to mass times acceleration due to gravity. So in this case, 15 kilograms times a negative 9.81 meters per second squared. If I plug that into my calculator, you can plug it into yours. Let's see if we get the same answer. 15 times negative 9.81. I got negative 147.15 newtons. All right, that's my F of G. But we learned that doesn't help us find the normal force. It also doesn't help us find our force going kind of in a downward direction. Let's say theoretically this is on a frictionless slope. I could figure out, with no friction, there's nothing pushing up on it. Gravity's still kind of pulling downward. So I know I need to find, let's see if I have straight I can do that. Kind of right over my thing I wrote there. All right. So we have FG of y and FG of x. All right. And I want to know really what I want to know. What's this guy? What's that? What's that force right there? Right now we know that's FG of x. All right, so now let's go through, let's solve this. All right. This triangle right here, the one I just added in, let's rewrite that. Let's go. Sound effects are optional. I think they make physics more fun. That is not a straight line. That one's better. All right, right angle there. We said f of g is 1 negative 147.15 newtons. All right, fg of y here, fg of x. All right, and we already went through kind of the trig to solve for these things. So, oh, remember this angle right here? It's the same as this angle right here because geometry, and we're not going to go through that again. All right, so in this case, if I wanted to find fg of y, we knew fg of y was equal to the force of gravity times, in this case, it was the cosine of theta. This time, though, we know these numbers, so fg of y equals, oh, let's go with negative 147.15 times the cosine of 35 degrees, and go to the calculator. All right, 147.15 times cosine of 35. Talking to myself. All right, in this case, I got 120.5. And forces in newtons. I should have put it in newtons there. All right, so Fg of y, 120.5 newtons. At this point, you can use Pythagorean's theorem to figure out Fg of x. Really, what I'm going to do, though, is I'm just going to do the trig again. I think trig gets us better answers. Pythagoras, though, does give us a way to check it. Fg of x, if I scroll up, we said Fg of x was equal to the force of gravity times the cosine of theta. No, sorry, I'm looking at the wrong one. Fg of x is equal to Fg times the sine of theta. So, went too far. So Fg of x equals, we said negative 147.15 newtons times the sine of 35. All right, math one more time. 147.15. Oh, let's make that negative, just because that guy's negative. Times sine 35. Imagine I'm going to get a much smaller number. Yeah, I got 84.4 newtons. All right, so in this case, if this is a sheet of completely frictionless material, I would know that it has a downward, a force coming down the slope at 84.4 newtons. Okay. So let's change the question a little bit. What if the brick wasn't moving? That means it's not frictionless. This means we actually have a force of friction. In this case, the force of friction opposes the force of gravity in the x direction or down the slope. In this case, the force of friction would just equal that. Or, if I said that's negative, then it would be positive 84.4 newtons. Or let's go back to it being frictionless. Essentially, once I have the force, I have the mass, I can figure out how fast this thing's accelerating down the slope. That's really important to know. If I'm loading up a moving van and all of a sudden my box of fine china of glassware is rolling down the ramp, I want to know how much time do I have to go catch it. I'm probably not actually going to calculate it, but you can see where it could kind of maybe be useful. These things do become really important in things like engineering, factory floor plans that involve apparati that operate at different heights. How fast can you send things down a slope to get to the next machine, stuff like that. Anyway, that's pretty basic. Good luck with the practice problems.